So thank you very much. I'll try and capture what we've been working on with this funding that we've been very fortunate to receive. Last summer, we recorded what I believe at this point remains the hottest average temperature over the whole planet that was been observed since at least 1940. So these little plots, I don't know if you can see all the little lines here, but they're actually showcasing what average temperature over the whole surface of the Earth is, taken by a bunch of different measurement stations. And you'll notice that we reached a very high temperature of 17.16 Celsius, which does not maybe seem that hot, but it is. And I like to always start my presentations with this because, of course, we think about climate change along many different effects. But the thing that I think motivates much of my work and what I am primarily concerned about is just the fact that it's getting hotter, which has a very direct consequence. So heat is, and this surprised me when I first learned this fact, but heat is actually the number one weather-related killer, at least in the United States. And usually we think of other natural disasters, whether they're fires or floods, hurricanes, things like that, but it's actually just heat waves. And this has a lot of really interesting and pernicious downstream consequences into who actually experiences the worst health consequences from heat. And so this was actually a news article in the New York Times in 2019 with a really evocative photo of a woman standing in the shade of this bus stop sign, because it turns out most of LA's bus stops don't actually have any shade, which has been shown up in the news in different ways over the last few years. It getting hotter just has an immediate human health consequence. And the fact of the matter is it is going to get hotter, and it is already hotter. And if we don't have a good way of keeping people safe outdoors, that's a basic problem. And it turns out we really don't. There's actually a very small portfolio of options and solutions we have accessible today. There's also a more scientific problem that arises when ambient conditions outside are on average getting warmer. And that arises from thermodynamics. And so, there's a lot that's behind the scenes here, but the short take of all this is that when our ambient conditions get hotter, the efficiency of every energy conversion process here on Earth is going to drop. So that includes your car, that includes power plants. It also includes air conditioners and refrigerators, right? This is why an air conditioner has to work extra hard, draw more power to deliver the same amount of cooling for an interior space when it's hotter outside. So that hopefully is intuitive, but the flip side, the fact that the efficiency of every thermodynamic process, which really means everything, including you and I, we all become less efficient, and they all become less efficient as air temperatures rise. And so this is a universal problem in addition to this direct consequence to human health. And so our approach to this is to ask what's the coldest thing that we have access to? And that is, of course, the cold of space itself. So it sits at 3 degrees Kelvin, which is around minus 454 degrees Fahrenheit or so. And wouldn't it be nice if we could access some of that coldness to keep things passively cooler here on Earth? Well, we don't quite have access to it, obviously, and it's a good thing. Otherwise, we wouldn't be alive here on Earth. But we do have some indirect access to it, and it's not through air movement or through conduction. It's through heat actually transmitting as a form of light that's known as thermal radiation. So this is something all objects emit as a function of what their temperature is. So your skin emits it, all the walls around us right now are doing it, and it's a kind of ubiquitous form of heat exchange that is mediated by light, by photons. It turns out our atmosphere does trap quite a bit of it. That's the greenhouse effect, and those are the greenhouse gases responsible for it. But quite a bit of it does escape, and if we engineer it correctly, we can actually get an entirely passive cooling effect that's known as radiative cooling. The way this actually arises is due to some natural properties of our atmosphere. So our atmosphere does block quite a bit of light that's emitted upwards from all of us, the soil, the roof, all objects around us. But quite a bit of it can escape. Now, on days like this, when it's cloudy and rainy, it's not really escaping. But on a relatively clear day, which we fortunately have a lot of here, quite a bit of the heat that is emitted upwards as light effectively gets out of our planet. And so this is a natural phenomenon. It's happening all the time. And you can convince yourself of this by just buying an infrared temperature gun, pointing it up to the sky, and you will see this effect. And so you can also think of it as heat transfer. So, the blue is what goes out, and the orange is what the atmosphere sends back to you. If you sum that all up, you get net flow of heat outwards. This is really the mechanism that we want to take advantage of to enable a cooling effect. So this concept has been around for decades, in fact, centuries, and it has been exploited by many peoples and cultures over time, but it never really took off as a practical approach. And the problem is we need cooling in the middle of the day during hot summer days in particular, and that's when if you're outside and facing the sky, which is how you can send heat upwards to outside away from our planet, you will see the sun. And so the sun's energy is much more intense, and therefore you need materials that are excellent emitters of this heat at infrared parts of the spectrum that are associated with thermal radiation, but at the same time, they reflect almost all of the sun's energy. So think of materials that are mirrors or white, but have the required infrared properties. And surprisingly, when I began working on this over a decade ago, there were no known demonstrations of this. And so 10 years ago, we demonstrated this for the first time using what's called you can think of it as an optical kind of thin film approach using vacuum vapor deposition. It is scalable and it had desirable properties. And the key thing that got everyone excited is you could keep a surface colder than the air temperature, even though the sun was shining on it outside. And it's an entirely passive effect. Very counterintuitive, but very exciting from a practical point of view. Since then, this concept has really caught the public's imagination. It has aspects of this have also been commercialized. Some of our past work was commercialized with startups. So if you go to the Target in Huntington Beach, it is actually partially radiatively cooled by films not too different from what I showed in that paper right there. So this is actually not a rendering. It's a real photo of an array of radiative cooling panels. They cool water. Let's see if I get this right. So they cool water running underneath here, and it goes all up right here to a heat exchanger, which then cools refrigerant in this unit of this store's refrigeration system. And so this is called a condenser. The refrigerant is cooled additionally by this water being flowed right out here. So all of this is to say there's a great deal of interest in materials that can achieve this kind of passive cooling capability, and in particular being able to do that in a very low cost and scalable way. Today, things have moved on, and the dominant paradigm we see today are polymer-based films and coatings. In particular, materials that use things like fluoropolymers, which are extremely durable under ultraviolet outside. And so a lot of great demonstrations of this, but there are some problems with this. And in theory, these are all scalable, but they have some fundamental problems. And so when we began approaching this at UCLA in around 2020 or so, we started thinking about paints. Right? What makes it so hard for a white paint you can buy at a hardware store? Why can't it achieve this kind of radiative cooling effect? It turns out the fundamental problem is really around this UV problem and UV absorption. So the primary pigments that is used for white paints is a material known as titanium dioxide. Pretty straightforward to use. It's been used for a very long time, but it's extremely absorbing of the ultraviolet. Now, historically, this has actually been a good thing, right? Because it absorbs the UV, it protects the rest of the paint's material, the polymer, the acrylic binder, from UV degradation. So people have historically said, hey, we're getting two things at once, right? Titanium dioxide protects our paint, and at the same time, it gives us the scattering of the light we need for it to be extremely white. If we want to overcome this problem and the limitations of traditional white paints for radiative cooling, it really comes down to thinking about that pigment, right? And saying, well, can we replace that pigment with something that's not UV absorptive? But the subtle thing that we've learned over the last few years is if you do that, you need to really worry about the rest of the paint, right? Not just the pigment that's in it, but also the binder, the binding materials, because traditionally, most of those binding materials are not by themselves UV stable or UV durable, and so they're not appropriate for outdoor use. And this is a very, very strange kind of thing. And if you talk to folks in the traditional paints and coatings industry, they would be kind of surprised if your goal was not to absorb UV. right? That is the dominant paradigm we see for outdoor materials. And so our approach initially was to simply replace the pigment with a UV reflective pigment, which is, say, a UV non-absorbing pigment. And so our two candidates are shown at the top right there. They're aluminum oxide and barium sulfate, both quite low cost and easy to acquire in powder form for, really cents a gram. What you see is that they overcome that dip in reflectivity that you see with the titanium dioxide. That's right here. Let me see if I can get this over here. Oops. So you see that solar absorption that occurs with our traditional white paints are now gone because the aluminum oxide and the barium sulfate just reflect over that part of the spectrum. And that, it turns out, is the key to making a white paint a super white paint that is capable of this passive cooling effect. So as we approached this, we realized there were some fundamental challenges in which this project really tried to tackle. The first is a question of how do you actually maintain this reflectivity long-term outdoors? So a typical use case might be, say, an outdoor space, a tent. It could even be the roof of a building. How do we actually practically use this outdoors? And one of the big challenges that the traditional cool roof material industry has encountered is that the reflectivity of materials outdoors drops. Due to degradation, due to pollution, things getting into the coating and material. And so over time, you see the reflectivity drop. And so if that happens for our materials, then they're not really worth using, right? Because the cooling effect requires reflectivity really above the 93, 94% point range. If you drop below that, then you might as well just buy a white paint at Home Depot, right? There's no benefit there. And so we need to solve that. I think the one of the key challenges with durability is UV absorption, and so we got to do this. But the other issue is that getting really high reflectivity requires very thick coatings, and that really adds to cost. And in particular, if we want to make these radiative cooling coatings, we've so far needed to use fluoropolymers as the non-pigment part of the paint, right? Paints have pigments and binders. The material the pigment is in and allows for light scattering. And fluoropolymers have a lot of regulatory issues right now. And if they're very thick, they get very expensive, and they're not really suitable for outdoor use. And so our approach to this is a rather simple one, and to kind of build on these concepts, which is to imagine a base coating, which could in fact be a commercial white paint that you can buy today, and to make it a bi-layer paint, and add on a thin UV reflective coating paint layer that is also protective and adds to the durability of the system. And so we think this is really advantageous because it really allows us to cut down on the total cost of the system. We can basically use a very cheap paint to do a lot of the solar reflection and that paint will also handle any leftover UV. And we have a very thin top layer that is, fractions of the total coating thickness, maybe only 5 microns thick, that has our special sauce of a UV reflective pigment in a fluoropolymer arrangement. And so, in our lab, we make a lot of these kinds of paint coatings, or my students do, not merely me. We have shown that, of course, you can make 97+% reflective paints that are around 100 microns thick, made from aluminum oxide and things like that. That's what these highlight. But that also we can start augmenting traditional paints that you might buy literally at the store. And so this is one example right here. You don't need to worry about all these details. This is wavelength, and this is the UV part of the spectrum. And what we're showing is that as we increase the amount of that top layer, we can, by design, have it increase its UV reflectivity and therefore its total performance. And so this is a mechanism for us to take a 91% reflective paint you can buy commercially today up to the 94 and up to even maybe the 97% super reflective regime at an extremely low cost, and we think an extremely practical way. We've also done a lot of durability studies outdoors to look at how adding this kind of coating on top actually preserves the durability of that kind of bulk layer that is responsible for where the degradation really happens, the base paint. And so we think this is very exciting and very practical. It solves like an immediate problem that is going to make this kind of technology useful. And so, you might want to know what this looks like. So if you actually put it outdoors, our super white paint will be significantly colder than a commercial paint. So commercial white paint will be above air temperature. This right here is below the air temperature. How cold it kind of depends on insulation and a lot of other things, but this kind of is the key signature we're looking for. And this is under direct sunlight on a June day, right? On a day where you have direct sunlight on it. So I want to conclude this by thinking broadly about what the impact of this kind of capability might be. So we had a separate project funded by the Sustainable LA Grand Challenge, which was on enabling outdoor spaces to be cooler. And so this approach used both the kind of materials that we've shown right here, as well as active cooling systems. And we actually did a demonstration in the San Fernando Valley with community members, with human subject testing, to look at how we could actually keep people cooler in outdoor spaces without cooling the air, because you can't really do air conditioning outdoors. And so this is a really interesting line of, the bottom line is we can actually keep people more comfortable and safer outdoors. It might not be as comfortable as being indoors, but it gets you pretty far along the way. And the kind of materials we've developed here, I think are really going to be part of that solution. So this is, for example, a rendering of a hypothetical kind of vision of where these kinds of materials could be used in outdoor spaces, along with other strategies to really enable what we call thermal comfort for people outdoors. So with that, I want to thank Aryan and Justin. Justin's right here, who are grad students in my group who worked on this, as well as Dr. Jyoti Mandal, who worked on this, and funding from this excellent program. Thank you.